Yeah, good evening, everyone. We are waiting for the participants to join. Please stay online till the speaker joins the session, and we are also waiting for the participants to join. Thank you. Yeah, good evening, Srinivas Rao sir. We are waiting for the participants to join.
Yeah, good evening.
Yes. We just within 3 to 4 minutes we'll start, sir. We are waiting for the participants to join.
Yeah, sure, sure.
Thank you. Thank you. Okay, let's start the session. Good evening, everyone. Myself, Vijayalakshmi, Associate Professor, Department of Electrical and Electronics Engineering, VJIT. Respected HOD ma'am, fellow teachers, and all the delegates, whoever are present here. A very warm welcome to the last day of International FDP on applications of power electronics in renewable energy sources and electric vehicles. Today, we have Dr. D. Srinivas Rao sir, Associate Professor, NIT Warangal, as a speaker of the day. May I now request Mrs. Srilata ma'am to introduce the speaker of the day.
Okay. Good evening, everyone. Dr. Dharmavarpu Srinivas Rao was born in Andhra Pradesh, India. He received the BTech degree from Bapatla Engineering College, Bapatla, India, in 2006, and MTech and PhD degrees in Electrical Engineering from the Indian Institute of Technology, Roorkee, India, in 2008 and 14, respectively. He is currently an associate professor with the National Institute of Technology, Warangal, Hanmakonda, India. He has authored or co-authored more than 20 research papers in various journals and presented more than 10 research papers in various international conferences. His research interests include power quality, multi-level inverters, modulation techniques for multi-level inverters, development of new converter topologies, electric vehicles, active front-end converters, and adjustable speed drives. Good evening, sir.
A very warm welcome, Dr. D. Srinivas Rao sir. I request you to take over. The session is all yours. Yeah, thank you, sir.
So good evening, everyone. Am I audible?
Yes, sir.
Yeah,
Yes,
you are audible.
you're audible.
Yes, sir.
So let me share my screen.
Yes, sir. Please, sir.
My screen is visible?
Yes, sir.
So good evening, everyone.
Good evening, sir.
Yeah. So today I will discuss about the battery chargers for electric vehicles. So you're aware of that this power electronics is used in everywhere, especially in automobile electronics. So starting from low voltage power supply to high voltage power supplies. So these power electronics are necessary. So if you can see on the screen there, so these are the various applications. So where you actually require electronics, especially power electronics, starting from low power to high power. So you can see all the applications starting from here. So we have windshield wiper control, heads-up display, and auto dimming, interior lighting, active noise suppression, right? So entertainment systems like playing music and all. So electronic tool collections, security systems, and other active and passive safety systems. Like for example, in case of passive safety system means controlling of this airbag deployment, and for active safety systems, for this we have this electronic stability control, hill hold control, and this other controls like engine start and stop, electronic valve timing. So all these things you require power electronic circuits, right? So here, so we are right now focused in there are numerous applications for this, especially when you talk about the electric vehicles. So one is the powertrain and the battery charger. So these are the major things, so that where this power electronics plays a major role. So in case of powertrain, you require a inverter and associated with a motor. So motor may be an induction motor or a PMSM motor. So in case of battery chargers, So that's what we are talking today. So here, this battery charges, again, you require power electronic circuits. It is a combination of AC to DC and DC to DC, and ultimately it is feeding or ultimately it is charging the battery. So it may be bidirectional or unidirectional depending on the application. Right. So this is the overview of this electrical power systems in electric vehicle or hybrid electric vehicles. So you can see here that, so this is the inverter, this portion especially. So you can see here, so this is an inverter, so which is feeding an electric machine, and so this is ultimately feeding to the drive shaft. So depending on the vehicle, it may be front wheel drive or rear wheel drive or all wheel drive. And this inverter is feeding from a battery. So this is the high voltage battery, so usually known as the main battery or the propulsion battery more precisely. Okay, so you can see the power flow. So from this battery to the inverter, from the inverter to the machine, electric machine, it may be PMSM machine or permanent magnet machine or brushless DC machine, or most cases we are normally using this induction machine. And it is connected to or it is coupled to the drive shaft. Okay. So now to charge this battery, so we have this setup. So based on these applications, we have two different charging mechanisms out there. So one is the onboard charging and off-board charging. So what is onboard charging means? So entire charging setup is inside the vehicle. So that is onboard chargers. And off-board chargers, so that is the charging setup is outside the vehicle and you will directly connect it to this battery. The off-board charge is directly connected to the battery, so whereas on-board charges, so that is, so we have some internal converters, so that will connect it to the high voltage battery and it will charge that. Right. So you can see here in this bottom, these are on-board chargers. So you can see here, this is single phase, so medium power charger, and another one is three-phase high power charger. So these two on-board chargers. So whereas we have this DC or ultra fast chargers, so this is off-board charging. So you can see, so it is directly connected to this high voltage battery. All right. So come to these charging mechanisms. We have the single phase medium power charger. Right. So this is your grid. So usually single phase supply in this particular case. So this single phase supply is connected to AC here, and this AC is converted to a DC, right? So after that, we have this DC-DC converter, so usually isolated DC-DC converter, and this isolated DC-DC converter is charging the high voltage battery. So you can see here, so this one is the high voltage DC bus. So where all this drive shaft, inverter, and this high voltage battery, so which are connected here. So this is in case of single phase. So whereas in case of three phase, this is the three phase supply, and this it is connected to the AC supply here, and this AC is converted to DC. Again, this stage is common, so this is the DC-DC converter stage, and it is directly connected to charge this high voltage battery. Right. So usually, so this one, so this single phase supply, so that is normally kept at in the home. So whereas this three phase supply, so it is usually at offices likewise, right? Okay. And whereas this one, so this is DC fast or ultra fast charger. So here, so everything is set up is inside or outside the vehicle. So we have this three phase grid. Okay, so from three phase grid, so we have this charger. So that means internally we have this AC to DC mechanism. So there internally, so where it will directly charge the battery. All right. So this is known as off-board charging. So it is usually, most of the cases we have this DC power charging, or we have this DC charges. Okay, right. So this is about charging the high voltage battery. So we have also this auxiliary battery, or also known as the low voltage battery, and it is usually, its voltage rating is around 12 volts to 48 volts. So depending on the car. So usually in luxury cars, so we have this 48 volt batteries is available. So in normal cars, we have this 12 volts batteries sufficient. Okay. So in case of internal combustion engine, so this battery is directly coupled to the drive shaft. Okay, this battery is coupled to the battery. So by using the dynamo principle, so this battery is charged. So whereas here in this case, so this battery must be charged from this propulsion battery, or also known as this high voltage battery. So to charge this battery, or to charge this low voltage battery, so we have this additional setup. So this is the high voltage bus. So from this high voltage bus, again we have this DC-DC converter. Okay, so from this converter we have other applications, like, so this is low voltage bus. So this one is the low voltage bus. So we have all these low power loads such as lighting of this one, or equipment, active and passive safety things. So all these things are fed from this low voltage battery, and this is used, this DC-DC converter is used to charge the low voltage battery, right? So whereas heavy loads like air conditioning and all, so that is directly fed from this propulsion battery, so where the power flow will be like this. So from high voltage battery, we have this DC to AC converter. So this AC is used in air conditions. So this is usually high power loads. So drive this high power loads such as AC. So we require this high voltage setup. So these are the internal power electronics. So that is used. So we have this AC to DC converters, DC-DC converters, and so other DC, again another set of DC-DC converters so that are used. So normally, so this is common. So these DC-DC converters are common most of the cases to provide the different voltage levels. So whereas these things, so these are exclusively for the electric vehicles. So now, so we'll start about the battery chargers. So these battery chargers are divided into two types. So one is conductive and inductive. So that is one classification. So this conductive battery chargers means, so we have a direct connection. So whereas this inductive, so that means the connection is through the induction principles. So there is no physical connection between that one. So based on the high frequency transformer connections, the power is induced on the secondary circuit, and so that is used to charge the battery. So this is one way of classification. So there is another classification is onboard chargers and off-board chargers, as we already discussed with it. Onboard chargers, so that means the entire charging setup is inside the vehicle. So just we need to give the single phase or three-phase supply. Okay, whereas for off-board chargers, so that is usually at the charging stations. So for that you need to give usually it is a DC one, right? And also we have this AC chargers or DC chargers. And another classification, so we have single phase and three phase. When it is talking about AC, so it may be a single phase or three phase. Okay. So this is one way of classification, and another way of classifications, so that is based on the power level, right? So we have three levels of battery chargers that are available. So one is the level 1 charging, level 2, and level 3 charging. So this next slide, it shows the different charging mechanisms and different international standards that are used for this AC to DC charging applications, right? Okay. So here, basically, these battery chargers are divided into most of the cases in the worldwide. So usually we have three standards. So one is the SAE. So this is the Society of Automobile Engineers. So this is SAE standard. So that is one. So another one is IEC standards, International Electrotechnical Commission standards, and another one is CHA-DEMO. So this SAE, Society of, usually it is US. So whereas this IEC, so that is usually European countries, and this is especially maybe in Japan. So these are the three charging standards so that are available in India. So there is no specific charges. So most of the cases we normally rely on this IEC standards. So come to this SAE, Society of Electromobile or Society of Automobile Engineers standards. So as we already discussed that we have this level 1 charging, level 2 charging, and level 3. Okay. Right. So this basically this level 1 and level 2 are onboard chargers. Level 1 and level 2 are onboard chargers. And this level 1, so this is usually single phase charging, and level 2, it is usually single phase or 3-phase charging. So you can see the power levels. So that is 1.4 kilowatt, right? So that is for level, it is usually less than 2 kilowatt. In case of a 3-phase, so it is usually less than 20 kilowatt. So to fully charge the vehicle, it normally requires at least 12 to 14 hours. So whereas in this case, it is usually require 5 to 6 hours to fully charge the battery. Okay. So another one is level 3 charging. So it is usually fast charging. Again for level 3, so we have this DC charging and AC charging. So this is especially AC charging. It is located off board, and you can see the power levels usually 50 kilowatt or 100 kilowatt range. Okay. So for this it will usually take less than 1 hour. It usually take less than 1 hour to fully charge the battery. So this is for AC. So again we have this DC charging. So level 1, level 2, and level 3. So remember all the DC chargings are, most of the cases, so it is off board only. Okay. So we have 40 kilowatt, 90 kilowatt, and 240 kilowatt. So that is, so you can see the current ratings. It is usually 400 amperes range. So for this, usually it will take less than 40 minutes to fully charge the battery. 40 minutes or 30 minutes to fully charge the battery. So this is all about the SAE standards. So whereas this IEC standards, so it is most of the European countries, so it will follow. So we have this AC level 1 chargers, level 2, level 3. Okay, so you can see that is 4 to 7.5 kilowatt. So whereas it is 8 to 15 kilowatt. And again, in case of level 3, so we have onboard chargers and outboard chargers are there. So you can see that 60 to 120. So whereas this rapid charging, so this power, you can see that it's 2000 kilowatt. So it is in the range of 2 megawatt. Okay, and it will take less than 10 minutes or 15 minutes to fully charge the battery. Okay. So this 2 kilowatt or this 2 megawatt chargers are usually used in heavy load trucks or heavy load electric trucks. And this is about the IEC standards. So whereas another one, so this is especially used in Japan and other countries like China and other. This is a CHA-DEMO. So this is one standard. So that is used in Japan especially. So this is, they have only DC levels, or this is especially DC chargers. There is no AC charging mechanism here. Okay. And here you can see the power ratings. So this is 120, this is 62.5 kilowatt, 125 amperes. And we have also this 400 amperes and 500 amperes. So even 1000 amperes current rating is also available nowadays. Okay. So these are the international standards for AC and DC chargers. So what we can summarize is that we have level 1 charging, level 2 and level 3 chargers, right? And we have these different standard protocols are there. So one is the SAE standard, IEC standards, and CHA-DEMO standards, right? And these are the different manufacturers or different industry. So where we have this fast charging solutions. So most of the industries, it's nowadays, this is everyone, most of the industries are coming with their own DC fast chargers. So this is previous data. This is one of the main one is the ABB, and another one is the Tritium and Ping Hong. So this is the Hong Kong one. So this is a Tesla supercharger. So EV, TEC, and this is again ABB. So you can see that. So this is what kind of protocol that is supporting. This is CCS type 1. CCS is the combined charging system. So we'll discuss in the next slides. Right. So this is also GTPD. This is another charging. And this is superchargers. So this is Tesla's proprietary one. And this is EVTEC. You can see that this is what it compliances with that. So this is SAC standards. And this is also supports the CHDA and again this is SAC combo and the CHDA okay. And these are the input range and the output voltages and their power limits, and this is to add extra every 200 miles. So how much time it will take. Okay, so this is usually the measure. So to add extra 200 miles, so how much time it is required. So that is one. So this, for this one it is 72 minutes. And whereas this one, this is only 10 minutes because this power level is around 350 kilowatt. So whereas here this is 50 kilowatt, so that's why it is taking roughly 72 minutes. And you can see that it is 50 kilowatt and this is 350 kilowatts, 7 times more wattage is there. So you can see that the time is reduced by 7 times. It's by 70, roughly 70 minutes, and this is roughly 10 minutes. So power is increased by 7 times and the charging time is decreased by 7 times. Okay. And as we discussed, these are summarises. So different safety standards for electric vehicles. So we have this SACJ and all these things so that are available. Okay. So these standards discuss about the different protocols. So how this you're aware of this in recent times, these electric vehicles are catching the fire, right? So most of the cases we are experiencing that. So right, so these are the standards because the main problem is that they're not following the proper standards, right? So these are all the standards so that usually discuss about the electric vehicle safety norms and charging norms and other things. You can see that electrically propelled load vehicles inside out, protection of a person on board is not described. Okay, electric shock protections, EV infrastructure safety and electric vehicle installation. So workplace safety, say this is electric shock protection, protection of charging systems and described. So all these things, okay. And this is another one, this is a very important one, safety rules for the recharge energy storage system, right? So this is discussed about how to charge the vehicle or how to safely charge and discharge the vehicles when it is used and when it is not used. So especially this standard will discuss that one. Right. Okay, so vehicles must be compliant so with these safety standards. So then only so it will be in the right operations. Otherwise, so we have as we already seen that it is facing a lot of problems nowadays. So these problems usually associated with one of the main thing is that there is a lack of proper heat dissipation inside the battery. So that is one reason. And another reason is using of recycled materials. Most of the cases, many manufacturers have come up with recycling the older batteries, right? If they're not properly recycled it, so there is a tendency that it may catch a fire. So come to this charging sockets, so our charging pins. So as we already discussed that there are different charging pins, so depending on the country of origin. So we have this SAC 1A 1772. So we have this L1 and L2. So this is single phase charger. You can see that this is phase and so this is neutral. And this is PE, so usually ground. And the CS and CP, so this is how when the charge, this is usually CS and CP, so this is control of pilot signals, so that is normally used to whether the charger is connected or it is disconnected, or that in kind of information is provided by these two pins. So this is for single phase, and the same thing for 3-phase. So you can see here L1, L2, and L3. So these are for 3-phase, right? Again, these 3 are used to get the data from the one, and this is the neutral wire, and this is the ground one, and this PP and CP are used to or control pilots. So that is pilot switches that is used to get the information about the charge and so how much percentage it is charged, whether it is properly connected or not. So those kind of information that is provided. So you can see that this is the combo chargers. You can see this is top one is for AC and this bottom one is for DC. Similarly, this is for AC 3-phase and this is DC. So these are usually known as combo chargers. Most of in India, so we are using this CCS, means combined charging system. Combined charging system. So in India, we are using this. So it may be single phase or 3-phase. So depending on that. So if it is connected to the DC, so this AC side will be locked. And if it is connected on the AC supply, so this DC side is locked. So that is combined charging circuit. That means we have AC and DC. So only one charging pin for both AC and DC. So this is another one. This is only for DC. Okay, so we have DC supply only. So this remaining terminals are used for other setup. So this is what this one. So we have this is only for DC, and the remaining is this control area network and CI and this DC plus and DC minus. So all these things are to gather the information about the battery, especially battery temperature and battery S4C. S4C means state of charge. So how much battery that is charged. So those kind of information. So that is available or that can be read from the battery by using this one. So that information is provided to the what we say battery management systems. So accordingly, the charging speeds can be increased or decreased. So this is another one, GTB. Okay, again this is a DC charger. Again this is Tesla proprietary DC charging mechanism. We have this DC plus and DC minus. Okay, and these 3 are still not known to us because this is a proprietary one. Right. So this is used for communication purpose. Okay. So these are the main different pins so that are available. Right. So come to power electronic converters. So what kind of power converters so that are used for charging these applications? Okay. So before that, so we need to see the overview of battery charging in electric vehicles. Okay. So we have the supply here. Okay. So this is AC supply. So this AC supply is converted to a DC. So AC to DC conversion. So that is the first step. So AC to DC conversion. So that is the first step. So for that, okay. So normally AC to DC conversion that is accomplished by a rectifier, right? So normally diode rectifier or thyristor rectifier. So in case of diode or thyristor rectifiers, so we have some drawbacks like low power factor. If the firing angle increases, the power factor it will be reduced, reactive power requirement, and also we cannot control we cannot regulate the output on the DC side if you are using a thyristor based rectifier, right? So the main drawback is the output voltage, it cannot be controlled precisely. Okay, so for that what we are using is that so power factor correction, PFC, power factor correction, AC to DC circuits are used, or AC to DC converters are used. So these are also known as active rectifiers. So that we will discuss in the next slide. Okay. So here this is input side filter. This AC and DC is converted here. This is DC link. So from this DC link, so we have this DC-DC converter. So usually isolated DC-DC converter. From that, again, we have this DC side filter. So again, it is optional. So depending on the power converter. All right. So it is ultimately giving to a battery. So this DSP or this microcontroller, so that will be controls these power converters. We have this is that's supposed to control this boost converter and DC-DC converter, and also it will control the filter size. So that means it will measure the currents and voltages, right? And it will control these 2 converters. So what essentially we have? So we have this AC to DC. Again, So this DC to DC. Okay. So this is usually known as front end. Okay, so this is back end. So from this, so it is connected to a battery. All right. So now, so what are the options that are available? So for front end converters, so for AC DC, so we have different options are there. So one is the bridgeless interleaved converters, so with power factor correction. So interleaved converter, so with power factor corrections. So bridgeless converter with power factor corrections. So conventional converter with power factor corrections. So these are all things are used to convert AC to DC. So that is one stage. So another stage is that back-end converter. So it is required a DC-DC converter, usually a isolated DC-DC converter. Right. So we have non-isolated converters. We have this buck converter, boost, buck boost. So these are usually this chuk converter, CP converter. These are non-isolated DC-DC converters. These 5: buck converter, boost, buck boost, chuk, and the CP converters. So these are the non-isolated DC-DC converters. So we have this isolated DC converters, so that would provide the galvanic isolation between the input and output. So this isolation is compulsory. So why? Because something is wrong with the AC terminals of the grid side, so that will not affect the battery or it will not affect the vehicle, right? So for that, we have this flyback, forward, push pull, and also we have this off bridge converter, full bridge converter, and this jet source convert, or this not jet source, this dual active bridge converters. So these are now usually isolated DC-DC converters. Okay. And we have another one is the resonant converter and jet source network converters. So these will be operated in 0 voltage switching and 0 current switching. So that use it to improve one of the main thing is that will improve the efficiency and also improve the electromagnetic interference, EMI problems. Okay. So 0 voltage switching and 0 current switching. So those are known as resonant converters. So when the voltage is, you're aware that the power losses, so which are associated with the voltage and current, right? So power loss equal to voltage into current, voltage across the switch and the current through the switch. So that gives you the power loss, right? So if you turn on the switch at 0 voltage or the 0 current, so that means one thing, for example, power equal to voltage into the current of the switch, on state voltage into current of the switch, right? So if one of the factor, if you make 0, so that means the power loss theoretically will become 0, right? So that is 0 voltage switching. If you turn off the switch or turn on the switch at 0 voltage instant, so in that case, what will happen? The power losses will be reduced. Similarly, if the current is, for example, the current is decreasing like that, if this is the current waveform, if you turn off the switch at this instant, right? So if at this instant, so that is 0 constant instant, so we can theoretically make the switching losses 0. So those things will be achieved by using a resonant circuit, so which is forming, which is using by the components L and C. Okay. Right. So we have direct conversion. Okay. So we have this direct conversion, this matrix converters, or this voltage source and current source in converters. So this is also used in this charging applications. We have this integrated charger topologies, where inside that we have this AC to DC conversion and DC to DC conversions. So that is inside that. And most of the cases, we are not usually use this direct conversions, especially this matrix converter, so which is directly convert AC to AC. So with the required, that means matrix converter is similar to what you have the cyclo converter. Okay. So first we'll start with AC to DC converters. So for AC to DC converter, as we already aware that it may be single phase or 3-phase, so depending on the power levels. So this is a conventional one, simple rectifier one by using diodes. Okay, so here it is a capacitor. The problem with this conventional one, right? So first thing is they produce a lagging displacement power factor, so with respect to the utility. And another thing is, so it can produce a significant current harmonics, right? And they can produce the DC with large ripple currents, and the DC output cannot be regulated. That means we cannot. It is difficult to operate in closed loop. And another one is limited regeneration capability. So these are the drawbacks of this conventional rectifier circuits. Understood? Right. So here, the single phase diode bridge rectifier. So this is the harmonic spectrum. So you can see that. So this is what this particular converter, so that produces the harmonics. This one, and this is what it is recommended values. So this IEC standard. So that's what it is recommended. Okay, so this is less than that. So that means in any industry or anything, so this kind of converters, especially in AC/DC applications, so these are, means we need to avoid these things, okay, to have this IEC standard. So that means all the vehicles or all the battery chargers, so those must be certified, and the certified is done by this IEC standard. Okay, so we have different, one is the CE, so Consumer Electronics Standard, and also we have this FCC. Okay, so the CE is usually for European Union, and this FCC is for US. So these two are the main one. So that means whatever any consumer electronics, or it may be anything, or it may be battery charger, or it may be mobile phone or smartphone, right? So that must be compliance by the CE or FCC, right? So they will thoroughly check that one, and they need to provide all the data. Okay, if all the standards they met, so then only they will allow for the release of that particular equipment, right? So this is not meeting the standards, so therefore manufacturers will never use this one as it is, and they're making some modifications. So with that, okay, so what kind of modification is that? This is active rectifiers, okay, so also known as PWM rectifiers. Okay, so these are developed based on the self-commutating devices. Earlier, these are developed with IGBTs or thyristors. So now these are developed with IGBTs or MOSFETs. Okay, so these are the advantages. So the unity power factor operation. So they draw the input current sinusoidal. They can produce the ripple-free DC, and we can reduce or we can regulate the output voltage and regeneration capability. So these are the advantages of these active rectifiers. So this one is a simple circuit. Okay, I'll quickly explain this one. So this is the simple circuit. This is also known as PWM boost rectifier. So almost all manufacturers use this PWM boost rectifier, of course, in different formats. Okay, so this is, so why it is known as boost rectifier means, so it is a combination of two things. So here, this one, if you see that, so this is a rectifier, simple diode bridge rectifier. Okay, other things, so this portion, so this is a DC-DC converter. What kind of DC-DC converter? So this is the boost DC-DC converter. So by combining these two, so this circuit is formed. Okay, so this is the one, this is the input, and this output one, so the output of this bridge will be a rectified one. Okay, so this output of this one is a rectified one. All right. See here, if the switch is closed here, so this capacitor is feeding the load. This is as similar to a boost converter. If the switch is open, right, so with this one, and along with the stored energy, along with stored energy in the inductor, so which is actually feeding the load. So this operation is simple or similar to a boost DC-DC converter, but the difference is for boost DC-DC converter, right, so we have AC here, so DC supply here. So instead of this DC, so we are providing a pulsated DC. Okay, so that is the only difference. All right. Okay, so you can see that, so when the switch is on, so this inductor current or inductor voltage, so this VL is L into dI by dt. So in this particular case, it is Vs by L if you apply KVL. So whereas here, so it will be Vs minus V0 by L. All right.
Yes, sir.
So it is Vs minus V naught by L. One second.
Yes, sir. Yes, sir. You may continue.
Yeah. Am I audible now?
Yes, sir. You are audible.
Yes, sir. Audible, sir.
Yeah. So here our objective is to maintain the unity power factor here. So our objective is to maintain the unity power factor. So when you say that unity power factor is achieved, so we have the source voltage here. The source current is also like this. So if both source voltage and source current both are in phase, so then you are aware that the source current, or you are aware that so unity power factor is achieved, and also the reactive power is 0. Right. So this is the source current. So what is the shape of source current here? So what kind of shape is, so you can see here, right? So if this is the one, so you can see a current something like this, right? So this inductor current, it's supposed to be like this, okay? So then only the input side current, so it will be like this, right? Agree?
Yes, sir.
This is the inductor current. Okay. So what? So how the inductor current will be very. So if this load is changes, the current will be changed. Okay. So what we have to do is, so we need to identify the peak value of this inductor current. So this again, this inductor current is depending on the load voltage and load value. So what mean, for example, if the load is increases, so this current is increases. Okay. Right. And another
Yes.
thing is that, okay, another thing is, so we need to control the current through this inductor. So you're aware that, so to control the current, so we have this hysteresis current controller. We have this hysteresis current controller. So you're aware, so how a simple hysteresis current controller will work. Okay. So when the switch is closed, for example, in this application, right, you can see. Yeah. So in this particular application, so when the switch is closed, right? So this is the one. So in this case, the inductor current is increases. Okay. So now what happening here is this inductor current, so which is feeding to the load side, right? So now the inductor current is reduces. So one side, so we have this positive value of di by dt, and other side you must have this negative value of di by dt. So you can see here, this is mod Vs by L. So that means this is positive here. So whereas here, so this must be negative to control the current. So when this will be negative, if this mod Vs, if it is greater than V naught, so then, so this will be negative. Understood? So that's why, so this output voltage, so that means the voltage, this output voltage, so must be greater than the peak supply voltage. So this is the supply voltage peak value. So this is Vm, right? So this V naught must be greater than this Vm. So then only this rate of change in the current. So one side we have this positive, and other side we have this negative, so that we can control the inductor current. All right. So therefore we have this controller. This is the reference voltage or the capacitor voltage, and this is the actual capacitor voltage. So this is given to a PI controller, and this will gives you I maximum value. So this gives you the I maximum value. right? So that means in this template, so what we have seen this, right? So this gives you this I maximum value, as we already seen that. So this is load dependent. So load dependent means the load is increases, so it must be given from the capacitor energy. So that means capacitor energy will be reduced. To maintain the capacitor energy as it is, so it must draw additional current. It must draw additional current, right? So this is right. This is gain. So now, so we need to generate this I maximum sine omega t. If you assume that the voltage is Vm sine omega t, okay? If you assume that voltage Vm sine omega t, the current is also I maximum sine omega t, so that the both current and voltages are in phase, and we can achieve the unity power factor operation. Okay, so this is the one. So what it can be? So it must be. So this is sine omega t, right? Okay. So this particular waveform is mod sine omega t. So if you multiply with mod sine omega t, so it will generate the current template for the inductor. So this is the inductor current template. So we are multiplying here. Okay, we are multiplying here by using the sine omega t. The sine omega t information is obtained from here. So by multiplying Vm, so this is, so by dividing this one with Vm, so we can get this sine omega t, mod sine omega t term we can get. So this is the reference inductor current, and this is the actual inductor current. By using the hysteresis current controller, so we can generate the firing signal for the switch, so that it can operate in two ways. So one first objective is the inner current control. So that means we are controlling the current and making the source current sinusoidal. And the second objective is, so we are outside current or outer voltage control. The outer voltage control, we are regulating the DC voltage. Okay. So that is what we get. We are regulating this voltage, and at the same time we are maintaining the unity power factor across the source voltage. So you can see the results here. So we are regulating at 400, and at the same time this is the voltage waveform, and this is the current waveform. At this particular level, the current is increased. So load current is increased. You can see the increase in the load current. Again, the load current is reduced. You can see that the load current is reduced here. Okay. It is maintaining unity power factor, and as well as the DC voltage is regulated. Understood? So this is how.
Yes, sir.
Yes, sir. So this is how it will work. So this is a simple one, single phase boost rectifier. So most of the cases, they may usually go for this one. Right. So there are another options, right? So there are another modifications with that one. So usually for achieving high power or high current applications, and at the same time, so reducing the size of inductor. So this is another one, is bridgeless PFC boost rectifier or boost converter. Okay, so here when you compare to this previous one, okay, so this is with bridge, right? So whereas this bridge is removed by adding another components. Okay. So by adding these two switches, the bridge is removed. So this is known as bridgeless power factor correction boost converter. So another one is the interleaved one. The meaning of this interleaved one is to increase the current rating. So most of the cases to increase the current rating, so we use this interleaved one. So you can see that there are two parallel paths for the current. So one path is here and another path is here. So that means once you have this DC diode bridge rectifier, so after that two boost converters are operating parallelly, right? So this forms one boost converter. So you can see here this one, this diode, and this capacitor will form one boost converter along with this switch. This is the switch. So this forms one boost converter. So again, so another boost converter, so which is formed by this LB2, DB2, and this Q2. So this is forming another DC-DC converters. So these two are operating in parallel. So usually 180 degrees phase shifted, so that the ripples will be reduced. and it is feeding usually higher loads. Okay. So depending on the current voltage, this is 2 converters are interleaved. So normally we have 3 converters, 4 converters are interleaving is available, right? So this is same thing with bridgeless. Okay, same converter. So we have this front end converter. This bridge is there, right? So this bridge is removed, and it is forming the same. So operation, this one is more or less same only. So it will eliminate some extra switches, and it will add some extra switches also. So the advantage here is that we have these 2 inductors are there, right? So most of the cases, these are the coupled inductors. Okay, so these are the coupled inductors. So why normally coupled inductors are used means, so you are aware that if the coupling inductors 2 are coupled, right? So there are 2 types of couplings are there, right? So one is the cumulative coupling and the differential coupling. So in case of cumulative coupling, if the 2 are, for example, it will be like this, right? So if it is a cumulative coupling, so if the dot notations are there, it is L1 plus L2 plus 2M. So the between this mutual inductance will comes into picture, so that the effective inductance value will be increased, right? So therefore, most of the cases we normally use this coupled inductor to reduce the size of inductor, and at the same time it will reduce the circulating currents. Okay. So both are same. So this is without bridge, right? So this is the comparison. Okay. So this is the comparison, right? So most of the cases, normally they will go with bridgeless interleaved converter with power factor PFC for higher current levels. So whereas for lower current levels or for cheaper solutions, so they will go with this conventional converter with power factor corrections, right? So it is less than 100 watts, they will go with this one, and it is less than 300 watts range, so they normally go with this interleaved choice. Okay. There are certain advantages, so the efficiency will be higher, and we can also increase this noise filter, and the ripple and the current also it's good. So when compared to this one, okay, the advantage with this one is cheaper one. So when compared to this bridgeless interleaved converter, right? So this is about this front-end converters. So these are non-regeneratives. So why it is non-regeneratives? Okay, if the load is active, so for example, this load is active, if we cannot have a power flow like this. Okay, so we cannot have a power flow like this because this diodes is stopping the power flow. For example, in this case, right, this is not a bidirectional one. So why it is not a bidirectional? If you want to have a current flow like this, so this diode is stopping here, right? And also this DC-DC, this diode bridge rectifier, this is also stopping. So these are unidirectional converters. So we have also this bidirectional converters. So these bidirectional converters are used especially so when it is operating, for example, if the car is equipped with some solar or solar panels are equipped with inside the car or inside outside the roof of the car, the solar panels are there, right? And under that case, so there is a chance that the power is fed back from the car to the from the vehicle to the grid. So we have 2 different operations, right? Vehicle to grid and grid to vehicle. Okay. So this kind of two to perform these 2, so we normally require a bidirectional converter, and this is the provides the bidirectional converters. So this is same as the H bridge or same as the full bridge inverter. It looks like an inverter, but its operation is entirely different. So inverters are normally used for DC to AC conversion. So whereas this is used for AC to DC conversion in bidirectional, right? So we have this AC supply. Okay, so output side we have this load, and when the 2 switches are these 2 switches are operated together, and and complementary to these 2 switches. Okay, so when these 2 switches are on, so we have increase in the current, right? So when we have negative decrease in the current, inductor current. So when these 2 are on, so we have increase in the current. So based on that, the inverter current, or based on that, the inductor current will be controlled. So you can see that. So this is having the what we say regeneration capability. So this one is the voltage waveform, and this is the current waveform. There are two things we can observe here. So one is the voltage and current waveform both are 180 degrees shifted. So that means the power flow in the opposite direction. So that is first thing. And the second thing is that what we say, you can maintain still it is maintaining the unity power factor, right? So this is cos 180 degrees. Cos 180 is still 0 only. Okay, so not 0. Cos 180 is still 1 only. That means unity power factor operation is achieving, and at the same time the power flow is negative. So nothing to do with that one. So when you have a negative power, if you want to operate in negative power, so what it should be, this voltage across this one should be greater than the load. Instead of that one, instead of load, if you connect a battery, something like this, right? The simple one, the DC generator is, for example, or the battery is connected, so higher value than this V0, so then the power flow will be negative, right? Okay. So this is, so what we can see that the battery charger, so complete battery charger. So you can see here. Okay. So this is the power supply. So we have this power supply and this EMI filter, so usually known as electromagnetic interference filter. So that means it will reduce the noise inside that equipment and also inside the converter, and also it will not interact, or it will not interact with the other converters. So we have this rectifier. So what we see in this, right? So we have this rectifier circuit. Okay. A small inductor or small capacitor is connected, so it is filter out that one. So after that we have this inductor power factor correction circuit. So this one. So this entire thing is forms a power factor correction circuit. This circuit is a boost rectifier circuit. Okay. So the DC is available here. DC voltage is available here, and this DC is converted to, our next stage we require a DC-DC converter here. So this is DC-DC converter stage. So this is DC-DC converter stage. So we have this voltage here. So this this DC-DC converter, so it is converted to high frequency AC. This is high frequency AC. So this is a high frequency transformer. Okay, HFTR means high frequency transformer. It is usually around 20 kilohertz, 50 kilohertz, or even 100 or 200 kilohertz, depending on the application. Okay, so normally why high frequency transformer used? So high frequency transformer, the size of the transformer will be very less. For example, if you have a 50H transformer, when compared to the 50H transformer, so it usually accounts for 5% of that one. For example, 50H transformer is weighing 100 kg. This high frequency transformer may be weighing for 5 kg or 6 kg, at max 10 kg. That's all. Okay, we can at least reduce 50 to 20, 50 times or 20 times of the weight and size of the regular transformer. If we further increase the switching frequency, there is a further reduction in the size will be achieved. Right. So this is a high frequency transformer. Again, this is DC is up, AC is obtained, right? High frequency AC. So to convert this high frequency AC, you have this, again this diode bridge rectifier is there. This is converted to DC. Again, we have some filters are there. So this filtering, and it is ultimately feeding to the battery. Understood? So we have this AC supply. AC is converted to DC, and DC, by using a high frequency transformer, this DC is converted. Okay, and it is ultimately feeding the battery. So what exactly inside that vehicle? So as we already discussed, that inductive charger and conductive charging. So if it is a conductive charging, right? So whatever these things are there, right? So here, so entire thing is, so if it is an onboard charger, so with conductive, so that means there is a physical connection, so between these things. So this entire thing, right? So this entire thing is inside the vehicle except this power supply. So this power supply is outside. So this entire thing is inside the vehicle. If it is an onboard charger, so this entire thing is inside the vehicle except this power supply. Just we need to give the AC single phase power supply. That's all. So all these things are available inside the vehicle. Right. So this is inductive charging, onboard inductive charging. If it is a conductive charging, right, or the wireless power charging more precisely, so in that case, so this thing is okay. So this is outside. Okay. This is outside the vehicle. This is off-board means outside the vehicle, and this is on board. So this high frequency link, right? So this high frequency link is used to separation, right? So we have this inductive coils are there. So that means the vehicle is exactly placed, and the power transfer is taking place. Understood? If it is
Sir,
off-board,
sir, one second. How we know, whether it is conductive charging or inductive charging? Like
that depends on the vehicle model.
okay.
So all are not, for example, your mobiles are there, right?
Yes.
Somewhere you are aware that mobiles, there are three different. One is the conductive, okay, normal one. Conductive means just we need to plug in so that the
Yes.
battery will be charged. So nowadays it is equipped with wireless chargers are there.
Okay. Yes, sir. Yes, sir.
So now we have on the back of the battery, we have some magnetic, some coils, copper conductors are available. So from that, the power is transferred. And also we have this reverse wireless charging.
Okay, like depending on this conductive and inductive charging, sir, will the cost be affected, sir? Like
yeah, cost will be more only. Okay, usually this conductive charger or this wireless chargers, usually the cost will be somewhat more.
okay, right. Thank you.
And we have this reverse wireless charging. So that means your mobile used to charge the another mobile or another gadgets, maybe earbuds or maybe your smartwatch or anything, right? So that is used to charge the your gadgets by using the reverse wireless charging.
Okay, okay, sir. Thank you.
So this is about that. And we have this another solution. So this is for bidirectional power flow. Okay. So this is a bidirectional power flow. Right. So we have this bidirectional DC-DC converter. So that means it is AC to DC conversion. So we have this DC is available, and this DC is converted to high frequency AC, and this high frequency AC is converted back to DC, and it is charging the battery. Okay. Right. So
Yes.
when it is used means, so when your application is solar or when there is a chance that the power flow is from back and forth, so under this particular case we use this. For example, you are implementing some regenerative braking. So in that case, so there is a chance that some of the energy is fed back to charge the battery. Under this case, so this is helpful. And also if the solar or if the roof of the vehicle is equipped with some solar panels, so in that case, during the day times when you left the car, and there is expect that it is used to charge or it is used the feed the power to the grid. So under this case, so these kind of charges are required.
That means each vehicle will have this both options, sir, like unidirectional and bidirectional, both, or any one?
Most of the cases are equipped with this bidirectional charges only nowadays.
Okay.
So why? Because after the invention of this is about in next class we'll discuss this, and next slide we'll discuss this. So this is the conventional one. Okay. There are drawbacks with this conventional one. So especially when you are applying the regenerative applications or another thing, right? It requires some additional DC-DC converter for regenerative applications. Okay. So if you have this kind of battery chargers are there, right? We can actually integrate that into the vehicle so that one converter will be reduced.
Okay.
Right. So here this entire setup, so this is known as dual active bridge converter, DC-DC converter. Okay. So this is also same. So this is known as not a dual bridge DC-DC converter. So everything is same, this except this active word is not there. So what this active represent means bidirectional power flow. Okay. So here one side you have this diodes and the other side you have this IGBTs or MOSFET, usually MOSFETs. Okay. So this allows the bidirectional power flow. This is dual active bridge converter. So nowadays almost all the electric vehicles, so those are equipped with this dual active bridge converters. So one of the main advantage means the power flow or the efficiency will be high, and it will provide the bidirectional power flow. To provide the bidirectional power flow. So that is the main advantage with these converters. Right. So we have this additional setup. So you can see here, right? So these additional components are there. So this LR, LM, and LR, this additional component. So these are used for zero voltage, ZVS, and ZCS. So this is forms a resonant circuit. So that means provide the zero voltage switching and zero current switching. All right.
Okay, sir.
So this is for three-phase. So we have this three-phase supply is there. Okay. This is three-phase. Okay. This is inverter. If you look, it look like a voltage source inverter, but its operation is different. Okay, this operation is different. So we have this voltage, and it's ultimately feeding the load. So we have this V reference, and it is controlling the. So everything is same. Slightly the control is a variable, slightly different. Okay, and you require these three inductors for that. So normally, for this three-phase supply, you require these three inductors. So most of the cases, this for PW require. So this inductor is must. So why it is must means, so we can control the current through inductor only. The simple idea is, so when you switch on the, or when you energize the inductor, the current will increase, right? So when you remove that, so the current will be reduced. So this is how DC-DC converters will work, right? So the current waveform will be something like that. So this is when you energize inductor, or when you feed that inductor, or when you use the stored energy to feed the load, the current will reduce. So this is positive di by dt, and this is negative di by dt, so that we can control the current by turning on and turning off. It is simple. For example, if you want to produce this kind of waveform, right? So we need to turn on that one. Okay. So once it's some limit is reached, after that we need to turn on, turn off. That means how it will be. So this is how the inductor current will be controlled by actively turning on and turning off. So that is known as what we say hysteresis current controller. For three-phase, you usually require these inductors. Okay. So normally what they come up with this one. So we have this machine will be there, right? Three-phase induction machine or current magnet machine. So machine having some windings. Okay, machine having some windings. Those windings acts as a inductors. Okay. So these windings will be acts as inductors. So when especially they use this three-phase power supply to charge the vehicle. So instead of these windings inside the vehicle, so they normally use these windings of the induction machine, for example, as a inductor for this front-end converter. So this is its control. This control is same. So you can sense the voltage here. So after that, so based on that, it will generate the currents, and it will generate the PWM signals like this. Different controllers are there. So one is, this is the there are many controllers are there. So one is the voltage current control approach. We are directly control the current, and we have another one is the space vector control scheme. Another one is the decoupled control scheme. So this is most commonly used. So we can have the individual control this active power and reactive power, and also we can control the DC link voltage, VDC or SP. So here the advantage here is that we can directly this is independent control. So decoupled control. So when you're controlling active power, so reactive power can be individually controlled. So that means the control of active power and reactive power both are separated. So this is what we use in induction machines. So in case of induction machines, we have separate control of speed and torque. Okay, that is decoupled. So when the torque is controlled, so you can maintain the speed constant, or we can maintain you can regulate the speed. Yeah. So likewise, so we have similar active and reactive power control. So this is decoupled control method. This is what commonly used one. So this is another one is the direct power control. So where we have a direct power control. So this is similar to the direct power control of induction machine. And if you want to go for high powers, right, high power applications, so we have this multi-level inverter, so which is known as active neutral point clamped or the direct clamped multi-level inverter, so which is used as a active rectifier. So another one, so this is the cascade edge bridge inverter, so which is used as a active rectifier. So this is the high voltage application. You can see that the voltage is around 6.6 kV. So depending on the power levels, so we have different options. We have low voltage options, and after that, this is for slightly higher voltage, this is for medium voltage, and this is for high voltage applications. Okay. So now come to this DC-DC converters, so for charging solutions. So as we already discussed that, the front end portion is over. So now we are moving to this DC-DC conversion portion. So we are all aware that we have different options are there. So we have this flyback, forward converter, so push-pull converters. So everyone has their own advantage and disadvantages. So most of the case, we normally use this push-pull converter or this flyback converter. Right. So we have the Chuk converter, CPIC converter. So but these are not isolated. And again, this half bridge and full bridge converters are used. And everyone is having their own drawback and their limitations. So before inventing this dual active bridge converter, so most of the cases they use this flyback, so either they use this flyback converter or this forward converter. So depending on the application. In case of this UPS applications or your home inverter applications, they mostly use this push-pull converter. So once this dual active bridge charges are available, right, so it is entirely changed. Nowadays, most of the manufacturers are using this DABs only. So as we already discussed that, so one is the bidirectional and unidirectional. So one you have this one. So we have this DC supply here. So DC supply here, and this is high voltage. So high frequency AC. Okay. So this is diodes are there. So that means this is non-regenerative. So this is same, but the thing is that so this is resonant. Okay, and this is dual active bridge, DAB, dual active bridge converter, and this is bidirectional one, and this entire thing is bidirectional. So whereas this is same, but we have this inclusion of this resonant components. Understood? So this is for unidirectional applications we use, and this is for bidirectional applications we use. Nowadays, almost all modern electric vehicles are equipped with this kind of thing only. Okay. So either with resonant or without resonant circuits, they're using this dual active bridge DC-DC converters with some resonant circuits to provide the efficiency. This entire thing is to provide some efficiency. So we have this DC supply, so DC supply, and this DC supply is obtained from the front end converters. Right. And this DC supply used to charge the battery or some other utility applications. Right. So based on this transformer and based on this turns ratio, so we can increase or decrease the secondary side voltage, so that we can match the transformer, not transformer, we can match the battery voltage. So depending on that, so we have, so as we seen that, so this is one H bridge and this is another H bridge. Okay. So now we need to see so how the power flow will be between these two. Right. So this is similar to a transmission line. So this entire thing can be modeled as a transmission line. Okay. So this is the one, and this is the output one, and this transformer so modeled as a inductor. Okay. So only the difference here is, so here this DC, right? So here it is producing a square wave. So instead of sine wave, it should be a sine wave, right? So instead of sine wave, so you have square waves on the both sides. So that is the only difference. So why it is square wave means, so this entire thing is operating in a square wave mode of operation. Okay. So when these two switches are on, so the voltage is positive. So when these two switches are on, the voltage is negative. So this is how the square wave is generated. But this is square wave is of a high frequency. Okay, understood?
Yes, sir.
Right. So how the power flow? So by maintaining an angle between these two, right? So in transmission lines, so how the power flow is happening? By maintaining a angle between these two, the power flow is happening, right? So for example, sending in power V at an angle 0. So if it is V at an angle some delta, so we have this formula V1, V2, right? So it is V1, V2. So V1, V2 sine delta by X. So that is the power. So that is being flown. Okay. So here, if it is lagging or leading, based on that, so we have power flow from this side and power flow from this side. So depending on the angle. So here also, what we have to see that, so means, so we need to maintain a phase shift between these two. We need to maintain a phase shift between these two so that the power flow will be, or power flow will be happen. If the phase shift is positive, the power flow may be in the forward direction. If the phase shift is negative, the power flow is in the opposite direction, right? If the power flow is positive, this is the direction, the positive power. For the negative power or negative phase shift, maybe this is the direction. That is the only thing, right? So based on this phase shift, okay, so we have different control techniques are there. So one is the single phase shift control, extended phase shift control, double phase shift control or dual phase shift control, and triple phase shift control. Dual phase shift control, single phase shift control, extended phase shift control, double phase shift control, and triple phase shift control. Right. So what is the meaning of, there are two phase shifts so between these two. So one is the outer phase shift and inner phase shift. So meaning of, so phase shift between these two, so that is outer phase shift. Okay. So if the one waveform is something like this, this is one bridge output. If the second bridge output is slightly lagging, okay, so that is known as outer phase shift. This is due to the outer phase shift. So this is leading and this is lagging. So that means the power flow will be like this, okay, depending on the current direction. So this is outer phase shift. Similarly, we have this inner phase shift. So this is two switches are complementary. Again, these two switches are complementary. So we can maintain a phase shift between these two so that the output voltage may be slightly modified. So instead of square wave, so you may get a quasi square wave. So if you have some phase shift between these two pulses, so that is known as inner phase shift. Similarly, we have this inner phase shift here. Similarly, we have this inner phase shift here. Okay. If there is no phase shift, so it will produce a square wave. If there is a phase shift between these two switches, it will produce a quasi square wave. All right. So now, what is single phase shift control? So what is single phase shift control? So that means the phase shift, there is a phase shift between these two. That means it is having only outer phase shift. So there is no phase shift between these two. There is no inner phase shift. Okay. So there is extended phase shift control. So means you have outer phase shift control, outer phase shift, and one of the bridge having inner phase shifts. Understood?
Yes, sir.
Single phase shift control, only outer phase shift. In case of extended phase shift control, one of the bridge having inner phase shift. In case of double phase shift control or dual phase shift control, so both bridges having inner phase shifts. Okay, both are having inner phase shift control, but their phase shift is equal. If this is having 30 degrees phase shift and this is also having 30 degrees phase shift, so that is dual phase shift control. In case of triple phase shift control, so this is, for example, the phase shift between the inner phase shifts in one H bridge and another H bridge are different. For example, this is 30 degrees phase shift and it may be 40 degrees. Okay. Understood. So that is triple phase shift control. So single phase shift control, only outer phase shift. Extended phase shift control, you have only one bridge having inner phase shift, and double phase shift control, two bridges are having inner phase shift and their phase shift is equal, 30 degrees or 30 degrees, for example. In case of triple phase shift control, it's everything same as double phase shift control, except that the inner phase shift controls are different. This is having 30 degrees and it may be having 40 degrees. So why these kind of complex things are there means, so we have to see the waveforms. So this is corresponding to single phase shift control. So this is originally invented. So this is extended phase shift control, and this is double phase shift control, and this is triple phase shift control. Okay. So these are the firing pulses for the switches S1, S2, S3, S4. That is the bridge one. So we can see that these are complementary here. So this is Q1, Q2, Q3. You can see here there is a shift between S1. So S1 is started here. So there is a shift here. This is the phase shift. Okay. So this is the bridge one output. So this is the bridge one output. And this is the bridge two output. So you can see that there is a phase shift between these two. So it is started at 0 here and this is started at 0 here. Okay. So this is single phase shift control. The drawback with single phase shift control is the circulating currents. So why circulating currents are there means, for example, this voltage, this is negative, and at the same time, so this value is positive. Okay, this value is positive. So if you write the KVL between these two, right? If it, what is the current through this one is, so V1, okay, vector, so minus V2 vector by this X. So that is the current that is flowing through this inductor. So if these two are same, okay, so then this value is 0. If these two are opposite direction, so in that case, this current will be double, right? So this current will be double. So in this case, so this is what's happening here. So this is negative, and at the same time, this is positive. So that means the difference between these two are more. So that means there is a chance that the circulating currents will be high. So this is similar to what we have studied the, in case of power electronics, we have studied the bidirectional, not bidirectional. Okay. What is it? There are two converters or opposite, circulating current mode control and a non-circulating current mode control will be there, right? So that is the one. In case of extended phase shift control, so this is reduced here by having some internal phase shift. Okay, so you can see that. So this is the first waveform and this is the one. So there will be phase shift here. So between this S1 and S3, see here, these two here. Okay, these two are not same. So you can see that there is a phase shift here between these two opposite switches. So based on that, so we have, there is a slight change in the output voltage. So earlier we had the square wave. So now we have this quasi square wave. Okay. Again, the secondary is same because we are providing only one internal phase shift. So these two are same. Understood?
Yes.
These two are same. Only the first H bridge output is slightly varied. This is varied, but these two are same. The advantage here is that, so this is 0, but at the same time this is some positive value, so therefore the difference is small when compared to this one. So here this is 100 volts, this is minus 100 volts, so that means the difference is 200. So whereas here this is 0 and this is 100 volts, the difference is only 100. Okay, so therefore there will be a reduction in the circulating currents. And this is DPS, double phase shift control. So we have inner phase shift control in the both H bridges. Okay, so this is the first H bridge output, and this is the second H bridge output, and this is the inductor current. Okay. So here the circulating current is almost 0 when compared to this. And we have this triple phase shift control. Okay, so where we already discussed that the inner phase shift is different. Okay, so here this is D1, this much of length is there, so whereas length is only this much. So this triple phase shift is ultimate one. So if you assume that the internal phase shift is D1, okay, this internal phase shift is D1, and D2 and D3 is the D1 is the outer phase shift, and D2, D3 are the inner phase shifts. So in that case, it is having all the three, D1, D2, and D3. Okay. In case of double phase shift control, this D2 equal to D3. Okay. In case of double phase shift control, D2 equal to D3. In case of extended phase shift control, any of this D2 and D3 is 0. Either D2 is 0 or D3 is 0. In case of single phase control, both D2 and D3 are 0. That is the difference. So this is the ultimate one. So this is the main one. Okay. So by appropriately setting D2, D3 values, so we can achieve either double phase shift control, extended phase shift control, or the single phase shift control. Okay. In most of the industries, or nowadays, more or less, they're using this single phase shift control only because of their complex. So now they are moving to either this double phase shift control. After that, many of them are now coming with this double phase shift control to reduce the circulating currents. There is a drawback with this triple phase shift control, means we need to control both D1, D2, and D3, right? Okay. So that is slightly different, difficult. So when compared to the single phase shift control or double phase shift control. Okay. So our ultimate aim is to increase the power transfer capability and at the same time reducing the circulating currents. Okay. So this is what we discussed. So now we have a soft switching solutions. So you can incorporate soft switching solutions for this one. So we have this different options are there. When you're talking about soft switching, we have this LC type. So this is the basic one. And also we have this LCL type. Also we have the CLCC type. So we have CL here, another CL here. And also we have this CLCL type. So this is symmetrical CLCC and asymmetrical CLCC. Different options are there. So this is a lot of options are there, and a lot of researchers are coming with newer solutions. Their objective is to increase the zero voltage and zero current switching, and also increase the range of zero voltage and so when you're talking about the ZVS or ZCS, so you must talk about the range. Okay? So normally, so when the duty ratio is changes, for example, internal phase shift is changes, the current waveform is also changes. In that case, the zero current switching is not achievable every time. Okay, so that's why they are coming with newer solutions, right? So this is the basic one, and they are coming with some extra components. This is objective is to increase the zero current switching or zero voltage switching range. For example, if the duty cycle is this is operating only for example 0.5 duty cycle to 0.6 only, right? So whereas this one, it may be ranges may be more. For example, it will be operating from 0.2 duty cycles to 0.9 duty cycles, something like that, for example. Okay, so entire range we can obtain the zero current switching. That is the objective, right?
Sorry for the interruption. Dear sir, sorry for the interruption.
Yeah.
I would like to add one more point here. Like the end goal of the soft switching solution is to increase the.
Yes.
You were mentioning that the end goal of the soft switching solution to increase the. efficiency?
Yeah, see only efficiency and the power dissipation.
So if we are increasing the efficiency, definitely we are eliminating some switching losses, right?
Yeah.
Yeah.
No, we are
Okay.
eliminating the switching losses, so that's why the efficiency is increasing.
Yeah. Okay, thank you.
No, we are eliminating the switching losses, so that's why the efficiency is increasing. So why efficiency is very important means, so these are operating at higher frequency, right? So when it is operating at higher frequency, the switching losses will be very high. So normally inverters are operating at the range of 5 kilowatt, 5 kilohertz, or at max 6 to 7 kilohertz. So whereas these are operating at 100 kilohertz or something like that. Okay. So if these are operating at higher voltage ratings, and also when it is 100 kilohertz, the size is also very less. So that means whatever the energy that is dissipated, right? So that must be effectively. So we need to cool down.
Okay.
And so these are the comparison of different types. So that is the traditional one. So that means there is no resonant. Okay. So in that case, so normally by default we can achieve the 0 voltage switching. Okay. But to increase the 0 voltage switching, we have options like LC type, CLCC type, symmetrical, and asymmetrical. Okay. So this is slightly complex. The symmetrical one is complex. So most of the industries either they use this LC type, or they make maybe they use this LCLs type, right? So our end goal is to achieve this 0 voltage switching and 0 current switching without affecting the normal operation. So when you are adding some extra components means, so obviously the loss associated with this elements will be increased. For example, you have LC is there, right? Again, you are adding one more capacitor here and one more capacitor, and you are increasing the inductors and all those things, right? So we have to make sure that, so that will not degrade the, or it will not increase the size, or it will adversely, and we have to make sure that it will not adversely affect the performance. Right? So this is about all these things. Same only. So thank you. If you have any doubts, please.
Thank you very much, sir. That was an elaborate lecture about applications of power electronics in electrical vehicles. You have started with the bridgeless, interleaved. You have compared all these things, and you have also elaborated on different control strategies, even the charged batteries. So everything, the flow which you have started from the starting till the end, it is well organized, and I think most of our participants have got their required information which they want regarding the electric vehicles. I request the participants to ask any queries or questions if you have.
Sir,
So if you
good
have
evening,
any
sir.
yeah, please.
Good evening, sir. This is Rajesh, sir, Assistant Professor, Triple Department, Vidya Jyoti Institute of Technology.
Yeah,
Sir,
please.
sir, when we are using these DC bidirectional converters in the chargers,
Okay.
as we find the number of components are increasing. So because of this, do we have any security issues, sir?
No, we have some. There is no much increase in the switching devices. Okay.
Okay, yes, sir.
So there is no much increase in the switching devices. Only two, three components are only increasing. So when you compare, so you are talking about this bidirectional one, right?
Yes, sir. Okay, sir. Sir, and one more thing, sir. Now
This is
is
the one,
level
right?
3.
Yeah.
Sorry, sir. Yes, sir.
So this is the one. Okay, this is the conventional one. So whereas this is the one. So with using this one, the number of components are so very much reduced. Okay.
Yes, sir.
So another
And
thing
sir,
is that most of the industries are so what they're trying to use that, so they want to eliminate the usage of especially this diode.
Okay.
Okay. So when compared to this MOSFET, so MOSFET the switching losses are very much less. So when compared to the diode usually have 0.7 on state voltage. So whereas
Voltage,
for
yes.
MOSFET it is usually 0.2 or 0.1 or 0.3. Okay.
Yes, sir.
So that is the
Yes, sir.
advantage.
Yes, sir.
Yeah. Please.
Sir, and one more thing, sir. When we are doing this fast charging, I mean this level 3 charging,
Yeah.
is it, I mean, safer, sir? I mean,
It is safer. It is using from several years and it is highly safer.
okay, sir. Okay, sir. And sir, can you throw some light on why the electric vehicles are now burning out, sir? Any, I mean, your insight into that, sir?
So why it is burning is as already discussed. There are several reasons. So one is
Sir.
they're not following the standards.
Okay, okay, sir.
We have already several standards are there, and inside
Yes.
the battery we have this battery management system is there. Okay?
Yes, sir.
What it will basically see that every time it will measure the temperature of the battery and also increase the, for example, some of the batteries are there equipped with some fans are there and some coolant will be there, some forced coolant mechanisms are there. So that must be
Yes.
properly used, that one. Okay, so different sensors are there to use to measure the temperature and all. That is a proper, it's not properly designed, so that is one of the problem. And another one is that using the recycled materials. So most of the cases there, especially for low cost, means low cost. For example, in case of two-wheelers, many of them are coming with some low cost. Their object is to reduce the cost. So for that, electric vehicles, one of the major component which is carrying the most of the cost is battery. Okay, so they're using some recycled material and they're not properly use that, not properly process that without the properly processing. So what will happen? It may cause some leakage, or it may be the inside the material inside. It is causing some heat dissipation or uneven heat dissipation. So that is usually causing the heat.
Good evening, sir.
Yeah, please.
Thank you very much, sir. Thank you, sir.
Sir, this is Srilata, sir. Actually, level 3 charging will damage the chemical properties of the battery, sir, since you say that it is fast charging.
No. So here, that will not damage anything. So if you are aware that, so for mobile chargers, okay, so earlier we have 5-watt chargers are there, right? If you remember that, it usually takes 2 to 3 hours to fully charge the battery. So whereas, so now all equipments are coming with different charging. We have normally we had earlier 30-watt chargers are there, 20-watt chargers are there, again 65-watt chargers are there, and 120-watt chargers, and 150-watt chargers, and now 200-watt chargers are there for mobile devices only. Okay.
Okay, sir.
Right.
One more question is, sir, the same connector can be used for a station as well as a home charging, sir.
That depend on so how it is employed. We already discussed the different chargers are there, right?
Yes,
Different
every vehicle is having one pin, sir, and one connector. The same connector can be used in the station as well as a home charging. Is it possible?
Yeah, that is possible. This is what these combo chargers are meant for.
Okay.
If it is station, it will work only for this. Okay, it is home, they will work with this. So this is 3-phase. So in India, they are coming with this kind of chargers, either this or this. Okay, either this one or this one. Okay, so this will feed anything. It will 3-phase. It will work for 3-phase, single phase, 3-phase, and it will also use for DC.
Okay, sir. One
So
more question.
Is known as combo connector.
Okay, sir. One more question. Then we are taking supply from the grid, sir. When we want to charge the high capacity battery, so there will be harmonics present in the grid side. So how to eliminate that harmonics, sir? Just by filtering or any other?
No. This is entire thing is for. It will not generate much of the harmonics. Okay. So if you use this kind of power converters, right, it will not generate any harmonic.
Okay.
So this is the source currents are signs. See, you can see here that. See here, this is signs. This is the currents, right? Yeah, this is ultimately feeding from the or ultimately drawing from the grid. So these currents are sinusoidal. You can see that these currents are sinusoidal, and it is in phase with. So here the THD is very less only. So that harmonic problem is not present. So when you use this kind of converters, when you have this kind of converters, so especially this interleaved or this kind whatever this kind of converters.
Means both voltage and the current will be in phase, sir, when we take supply from the grid.
Yeah, both will be in phase, and the current is also sinusoidal. So you can see that the current is sinusoidal. So only some high frequency content will be there, so that you can easily eliminate.
Okay.
Harmonic problem will not be there. Reactive power will not be there. So those problems will not be there. Okay. Power quality problems will not be there.
Okay, sir.
So only problem is when you are connecting several battery charge, several electric vehicles, or when you charge several electric vehicles at a time. No? So there may be some slight impact on the grid. It may be happen by draw. It is drawing excess current, right? So there is chance that it may draw uh, some voltage may be reduced or something. Those kind of problems may arise.
Okay. Sir, when we charge from battery to battery charging, there will be any losses, sir, from the station battery to the EV battery?
So obviously, it will be lost, right? So when it is charging cycle, so it is one battery is discharging and another battery is charging means. So those are equipped with some internal resistances. So there will be some loss.
Okay, sir. What will the capacity of the station battery, sir?
Station battery means it is depending on the means normally station battery means what you are trying to.
Means we charge the high capacity battery from the grid and keep it charging throughout the night, and that same battery can be used for charging EV batteries. Suppose I assume that there are 10 cars, 10 EVs arriving into the charging station. So I have charged the battery and kept it ready for the use.
So now how EV chargers or how electric vehicle charging stations work means they usually not having most of the times they're not having any charger. Okay. So what they have to do is they directly charge from the grid.
Directly charging from the grid, sir.
Yeah. They'll not use any intermediate batteries to charge that one. Maybe for power backup they use that charge battery setup. Okay.
So,
It is not like that from the grid they will charge the battery. Okay. Again, the battery used to charge another set of batteries. They will not use this kind of steps. So directly they will charge from the grid to your vehicle battery.
So morning times it is possible to charge directly from the grid, sir. EV battery.
EV battery morning time it will directly charge. Okay. So whatever the power comes from the PV, so that is directly injected to the grid. Okay. So from the grid it is charged the battery.
Okay. Okay, sir. Thank you, sir.
Thank you, sir. Any more questions from the participants?
Any questions?
Okay, sir. I think they are done with the questions. Thank you very much, sir, for the wonderful session. May I now request Dr. C.N. Ravi, sir, to propose the vote of thanks and the concluding remarks of this International FDP on applications of power electronics in renewable energy sources and electric vehicles. Over to you, sir. Ravi, sir.
Thank you, madam. First of all, I'll thank today the resource person. The sir readily accepted our invitation. So our colleague Morgan sir have approached, and today guest speaker is readily given acceptance and given time for us to deliver the lecture, excellent lecture in this today International FDP. So thank you, sir. Thank you for the acceptance and deliver the lecture.
Thank you. Thank you for giving this opportunity for this interaction.
Thank you, sir. I'll thank HOD madam and all the colleagues who are directly and indirectly involved in this FDP. And I thank all speakers who have given their valuable time for the last 5 days. Today is the 5th day, so last 4 days, all the speakers have given their acceptance and they delivered their lectures in renewable energy system and electric vehicles. And now coming to the conclusion remark. So we have a good response for this international FDP. This is our second FDP conducted in the department. So all the part of the India from Telangana state, Andhra Pradesh, Tamil Nadu, Kerala, Maharashtra, all part of the India, the participants have joined. and they have effectively utilized their time. And from abroad also 2 faculty members have joined, and 3 speakers from abroad, they given their lecture in this FDP. So thank you all the resource persons and the management who given the permission and this opportunity for the EEE department to conduct this second time International FDP. And most importantly, our constant encouragement is our participants. So all the participants have joined on an average per day 35 to 40% is 40 participants are joining and they're listening our FDP. So thank you one and all who are involved in this international FDP. Thank you one.
Thank you,
Sir, Ravi,
sir.
sir, thank you, sir. I would like to thank everyone, sir, as a participant. The 5 days were wonderful, and I thank all the speakers of all the days for giving a wonderful insights about the technical aspects. And also I thank Mohandas sir, Ravi sir, and Vijayalakshmi madam for their efforts for bringing out wonderful speakers for all the sessions. Thank you all, sir.
Thank you, sir. I request the participants to find the feedback form which is posted in the chat box. You may fill the feedback, and if any participant or the delegate want to respond to this FDP, you may respond. Please.
So thank you, everyone. I'm leaving.
Yeah, thank you, sir. Thank you for your valuable time. You may leave, sir. Thank you. Any participant want to respond about this IFDP? You may respond. Okay, thank you very much for patient listening. Have a good day. Thank you very much.